Say about magnetic field induction due to a bar magnet on its axial line. What is axial line? The line which is passing through north and south poles of the bar magnet, nothing but axis of the magnet only. If you take a point P here, which is r distance from the center of the magnet, and what is a resultant field intensity or resultant field induction at this particular point. Here for this bar magnet we have two poles, south pole and north pole, both have same strength M and M. And first we will calculate what is a field induction due to north pole and what is field induction due to south pole. To calculate field induction at a particular point, you should assume unit north pole here. Why? Because what is magnetic field induction means the force experienced by unit north pole at a particular point. That what you call field induction at that point. So here you can assume unit north pole 1n. This north pole repel this. That's why field due to north pole is acting away from the bar magnet, and the south pole attracts. It is acting towards to the bar magnet. Here in vectors, I draw here longer line for Bn, field due to north pole, and a shorter line for Bs. Because south pole is far away from this point, it creates less field here. So Bn, Bs are opposite direction. If you want to calculate total field, that is B axial, we can calculate the difference of these two fields, that is B axial equal to Bn minus Bs. First we will calculate what is field intensity due to north pole. So field due to a single pole, mu naught by 4 pi m by distance between the point and the pole. Here to here distance is r and this distance is L. Why? Because this total length is 2L. So here to here L. So L length short is there. That you get from here to here r minus L whole square. Distance is square place. In case of south pole, what you get from here to here r plus L is there. That's why you get for south pole, magnetic field due to south pole is mu naught by 4 pi m by r plus L whole square we get. Now we know Bn minus Bs you have to take for resultant field. Then mu naught m by 4 pi take common and you get equation like this. Make it LCM. And you get mu naught m by 4 pi, that is r square minus L square whole square you get. This is a plus b whole square minus a minus b whole square format. So we can write like this, mu naught m 4 rl by 4 pi r square minus L square whole square we get. This 4 rl pointedly we are writing like this, that is b axial is equal to here 2 into 2 lm. This latter we can write as a capital M, magnetic moment. So this is the formula, magnetic moment m bar, and magnetic field induction on axial line of the bar magnet is equal to mu naught by 4 pi 2 m r by r square minus L square whole square we get. You see these two vectors here. So here we can say the magnetic on the axial line, you see that magnetic movement direction from south to north. So the resultant field also acting from south to north, that means in the same direction as magnetic movement it acts. But because Bn is more than Bs, so resultant field is acting away from the magnet. Even if you choose a point here and south attracts more stronger when compared to, if you choose a point here, south attracts more stronger because it is very nearer and north repels with less force. So force is acting in this direction, nothing but field is acting in this direction. In this direction means where to where it acts like this, south to north. Here also it acts like this only. So on axial line everywhere, not only this side, that side also, everywhere on axial line field is acting in the direction of magnetic movement, that is from south to north. If you choose a short bar magnet, if you take a short bar magnet, in case of short bar magnet, take L is less than R. So when compared to this distance from here to here R and here to here L, If L is very very less, then put L value is equal to 0 in the given equation. Then what you get? R square whole square R power 4. Here R is there. You get R cube. You get. We know that here B and M are parallel. So on axial line, field is the same direction as magnetic moment. Now we'll see magnetic induction due to a bar magnet on its equatorial line. Equatorial line at a distance r from the center of the magnet. Assume a particular point P here, and what is the distance of the pole? Each pole from this point means, from here to here r, and this total length is 2l, here to here l, and this distance is root r square plus l square. This also same. And magnetic moment M is equal to 2L into M. Now first we calculate field intensity due to north pole, field intensity due to south pole. This where you calculate field intensity, there you have to assume unit north pole. You know that this unit north pole repelled by this north, so field due to north pole is away from the north pole, Bn like this. But this south pole attracts that, that's why the field due to south pole is acting like this. So now you see, and this is a triangle, isosceles triangle. Here two angles are same, and here you see, if these two angles, if you add, that we get 2 theta, that is exterior angle. Sum of interior angles is equal to total exterior angle. So what is angle between BN and BS here? That is 2 theta. Now we'll calculate what is the magnitude of BN and BS. So BN, field due to north pole. What is the strength? M. So mu naught by 4 pi. M by what is the distance of square? Here root is there now. That square and root get cancelled. You get R square plus L square. Due to south pole also same magnitude we get. Direction is different but distance is same and strength of the pole also same. So we get the same value. Here we can say Bn and Bs both in magnitude are equal. So two vectors Bn, Bs, and angle between those two is 2 theta. Then what you get? Resultant field. So B equatorial is equal to 2B cos theta. What is theta here? Angle between those two is 2 theta. 2 theta by 2. So it is 2B cos theta we get. And B value already we calculate, that is mu naught by 4 pi M by R square plus L square is Bs, and Bn, B all are same. That value we can substitute here in place of B. And cos theta. And cos theta using this isosceles triangle, use this angle cos theta. Cos theta nothing but adjacent L by hypotenuse root over R square plus L square. So cos theta is equal to L by root over R square plus L square. This value you can substitute here, and what you get in the equation, in place of cos theta take L by square root of R square plus L square. Here you see 2L into M, that you write at a place, and here you see this is X, this is root X like. Suppose if this something, this total is X means this is root X. X root X means you can write X power 3 by 2. So here R square plus L square whole power 3 by 2 it become. Now in place of 2Lm we can write capital M here, magnetic moment. So what is magnetic field induction due to a bar magnet on its equatorial line or bisector line? That is B equatorial is equal to mu naught by 4 pi M by R square plus L square whole power 3 by 2. Suppose if you take a short bar magnet, in case of short bar magnet what you can take? Put L equal to 0 in that case. So if you take L equal to 0, then you get R square whole power 3 by 2, you get R cube. And in this case field we are getting opposite to magnetic moment direction. Why? Because you see in the diagram what happened here. See here magnetic moment direction from south to north like this, south to north in this direction. But B equatorial we are getting like this, Bn and Bs, and you get exactly between these two we get. Why? Because these two are equal, that's why you get between those two. So this is opposite to magnetic movement direction. Magnetic movement from south to north. This is on opposite direction. So we can say on equatorial line, field is anti-parallel to magnetic movement or opposite to magnetic movement. Opposite to. Okay. So opposite direction. Now we'll see what is magnetic field induction on axial line for a short bar magnet and what is magnetic field induction on equatorial line. On equatorial line, we get this is the magnitude mu naught by 4 pi m by r cube. On axial line, here you get 2. This is on axial line. You see mu naught by 4 pi 2 m by r cube here. There only m by r cube, here 2 m by r cube we get. From this, what do you say? Magnetic field induction on axial line is approximately equal to 2 into magnetic field on equatorial line. If you take same distance means. Same distance means you see, suppose if you take a point here which is r distance, here also a point you can take r distance. At same distance, one is on axial line, other is on equatorial line. Then field here to here, field is here b means here you get b by 2. You get half of the field when on axial line is field is 2 times on equatorial line. So b axial is equal to 2 times of b equatorial we get. See some applications on magnetic field induction on axial line to equatorial line. For example, you can take a bar magnet and magnetic moment is m and we get at a particular distance r from the center at a point P and you get magnetic field induction B is equal to BI gap. Why? Because field on axial line is acting in the direction of the magnetic movement from south to north, so it also acts like this. So like this means this is x-axis, that's why we can write BI gap. If this magnet is rotated in anti-clockwise direction, this is rotated in anti-clockwise direction. If the magnet initially like this, now it is rotated like this 90 degrees, then what happened to field at this point? We know that last time it is a point on axial line. Now for this bar magnet, for new position, that is equatorial line. Then what happened to field? What is the relation between B axial to B equatorial? B axial is equal to 2 times of B equatorial. First they give B axial, we need B equatorial, so send this to that side, you get B by 2. B by 2 we get. But what is direction? What is direction? When north and south is there, you know that here field lines, you see, now this point is on equatorial line. On equatorial line, what is the direction of the field? Opposite to magnetic movement. So you see magnetic movement is south to north, upward. Now it is acting downward, like this it acts. So B dash is equal to field is half of that of on axial line and direction is vertically downward. Downward means here minus J you can take. In the same case, what happen if the magnet rotate in clockwise 90 degrees? This is a magnet like this. It will be rotate clockwise 90 degrees like this. If it rotate clockwise, then what happen? Initial field BI already we discussed. Now if it rotate like this means here field become half of initial field. Why? Because last time axial line, now it is equatorial line. But what is a field direction if the magnet is in this position, new position? You know that field is acting opposite to magnetic movement. Magnetic movement is vertically down, south to north, so it acts upward. Upward means plus J direction. That's why field is B by 2, but direction is plus J. And third case, if the magnet rotate 180 degrees. If the magnet rotate 180 degrees, then you see here field direction is reverse, but strength is not changing. Why? Because magnet it will be like this or even rotate 180 degrees. This line is axial line only, it is not changing. So on axial line field is B means here also B only, but direction only different. But because last time south to north is like this, so field is like this in the same direction as magnetic moment. Now south goes here and north comes here, so direction of the field changes. That's why I get minus BI. Location of null points. Now we'll see magnetic field induction due to a bar magnet at a point where the position vector make an angle theta with the magnetic movement. Magnetic movement direction from south to north like this, and this is the position vector which is r distance to a point P, and here that means we can take anywhere around the magnet. What is a magnetic field induction? To calculate that, we are assuming a line, a point here P at this particular point. Here distance is r and angle is theta. And to get expression for magnetic field induction at particular point, this magnetic movement we are resolving into two components. You see, along this line, this is the magnet means, so along this line we can resolve m cos theta. Perpendicular to this line we can resolve m sin theta. So here m cos theta and m sin theta. You see, this is the point P for m cos theta axial line, and point P is for this m sin theta, that is equatorial line. You see, like this is the equatorial line perpendicular to this magnet and parallel to this magnet. That's why for first magnet 1 it is axial line, for this one it is equatorial line. And what is the formula for axial line magnetic field induction? Axial line due to first bar magnet at this particular point, V1 is equal to mu naught by 4 pi 2m cos theta by r cube. Why? Because magnetic moment is m cos theta. That's why we get m cos theta. On axial line we get 2 here. And for second magnet, what you get? Mu naught by 4 pi m sin theta. Magnetic moment is m sin theta, but that is on equatorial line. Thus we get only m sin theta by r cube. 2 is not there because equatorial line here. And these two fields, you know that, and field due to first bar magnet, that is m cos theta, which is acting along the magnet, means like this we get. And second, due to this we get opposite to the magnetic movement. Suppose south to north like this, means it acts like this. That's why B2 we can take like this. So what is angle between these two? These two is making an angle 90 degrees here. B1 and B2 are making 90 degrees angle here. What is a resultant field? Total field at point B is equal to square root of B1 square plus B2 square plus 2 B1 B2 cos 90 becomes 0. That's why what you get here, square root of B1 square plus B2 square. And B1 B2 values both we know, and common terms I took here, mu naught by 4 pi m by r cube. And what remains there? Here 2 cos theta, here sin theta. 2 cos theta whole square plus sin square theta. And wantedly we can write 4 cos square theta, I can write as 3 cos square theta plus cos square theta plus sin square theta. 1 cos square theta plus sin square theta, it become 1. So 3 cos square theta plus 1 is there under root. So this is the magnitude of the resultant field due to this bar magnet anywhere, that is if the position vector make an angle theta with the magnetic movement. So at this particular point, what is the field means? This is the point. Suppose if you take a point on axial line means what is this angle? 0. Put in this equation, we get 0 here, cos 0 you get 1, and now we get 3 plus 1, 4, root 4 means 2 you get. What you get? Value mu naught by 4 pi 2m by r cube we get. We know that is a formula for magnetic field induction on axial line of the bar magnet. Suppose if you take on equatorial line means this line here angle it make 90 degrees like this, means equatorial line. Then you can take theta is 90, cos 90 is 0, then you get root 1 you get. So what is the total field? Mu naught by 4 pi m by r cube only. And this is the equation on equatorial line. And now we'll see what is the direction of the resultant field. So here they are calculating direction of the resultant field with r bar. This is a r position vector with respect to this. What is the direction of the resultant field? That direction you can take it as alpha. So one is adjacent, other is opposite, because these two are 90 degrees. So adjacent, opposite. What is tan alpha? Opposite by adjacent, B2 by B1. So B2 by B1 you can use. So what is B2 here? B2 is m sin theta by r cube. All are same. Here only sin theta, here 2 cos theta is there. So sin theta by 2 cos theta, that is half tan theta we can write. The relation between angle made by the position vector with magnetic moment and resultant field make an angle with respect to position vector. Now sometimes they can ask what is angle between magnetic field induction B bar and magnetic moment M bar. See that here resultant field make an angle alpha, here opposite angle also alpha, and this angle is theta. And what is angle between this is, you see, this is M bar, because always it acting from north to south to north in this direction, and BP is acting like this, extend like this. You see BP direction is like this. So what is angle between these two? Sum of interior angle is equal to exterior angle, that is theta plus alpha you get. So what is the angle between magnetic field induction, resultant magnetic field induction and magnetic moment, that is theta plus alpha you can take. Now see, if you place a bar magnet in uniform magnetic field and how it is experience force, how it experience torque, that we'll see now. First we'll calculate moment of couple or torque we can call, how moment of couple acting on a bar magnet placed in uniform magnetic field. So assume uniform magnetic field is there, that is B bar, and these are parallel lines equidistance. A magnet is placed like this. You see north pole try to move in the direction of the field and south pole move opposite to direction of the field. What is the force it experience? We know if you place a pole, magnetic pole inside magnetic field, F is equal to Bm. So that much force is acting on north pole upward and here south pole downward. So what is couple acting? Couple means you see a body is like this, and here one force is acting upward, other force is acting downward. It start rotating like this. So here these two forces are creating torque. So what is the torque formula? The perpendicular distance between two parallel forces into any one of the force. Parallel force means anti-parallel. Actually one is down, other is up. So what is perpendicular distance? Extend this force. Here Bm and here also Bm. Suppose if you extend this line backwards, this is the perpendicular distance between those two forces. So the perpendicular distance into any one of the force here you can use. What is torque or couple? Perpendicular distance between the forces into any one of the force. So what is perpendicular distance? You know from here to here 2L is the length of the magnet. And if the magnet make an angle theta with the magnetic field and alternate angle, this also theta. So we need a relation, that is x we need, but because this only perpendicular distance between the two forces. So hypotenuse we know 2L, from that x equal to 2L sin theta. Actually sin theta is x by 2L, from that we get x equal to 2L sin theta. We know perpendicular distance and force also. Substitute in this equation, perpendicular distance is 2L sin theta into force is Bm. Write properly 2Lm into B sin theta, that we can write as torque acting on a bar magnet which is placed in uniform field is tau is equal to mb sin theta. So that we can write as m bar plus b bar. Using this equation we can define magnetic moment of a bar magnet. How we can define m is equal to tau when b is equal to 1 and sin theta equal to 1. That means how they define magnetic moment of a bar magnet is equal to torque acting on it when it is placed in uniform magnetic field and normal. Normal means theta is 90, that's why sin 90 become 1, and uniform magnetic field means b also 1. Then what you get? M is equal to tau. So like that we can define magnetic moment also. Magnetic moment other definition also there, that is magnetic moment m is equal to 2L into small m also there now. So it is a product of pole strength into distance between the two pole strength. It is a product of pole strength and distance between two poles. And this is another definition. When we get maximum torque, when we get minimum torque. If the magnet is parallel to the field, if the magnet is parallel to the field, so sine 0 means you get 0 torque. If it is 90 degrees, you get maximum torque. 180, again sine 180 is 0, so you get 0 torque. And fourth case, if you take that is 270 degrees, theta is equal to 270 degrees, torque is equal to minus mb we get. Why? Because sine 270 is minus 1. Now we'll see different cases on couple acting and force acting on the magnet when it is placed in the field, magnetic field. First, we are placing in uniform magnetic field. In uniform magnetic field, we know how much force is acting upward, that is F is equal to Bm, and downward also same force is acting, F is equal to Bm. Both forces are equal magnitude in opposite direction. Net force acting on that is 0. If you place a bar magnet inside uniform magnetic field, definitely the force acting on that is equal to 0. And torque depend upon the situation. Already we discussed, angle between the magnet and the field is 0 or 180, you get 0 torque. For other all angles, it experiences some torque. That means we can't say that torque is 0. Torque may or may not be equal to 0 when you place a bar magnet in uniform magnetic field. What happens if you place a bar magnet in non-uniform magnetic field? Here convergence takes place, cloud lines, here rare lines is there, so here field is less, here field is more. That means here force is more, here force is less. Because of different forces, what happen? Net force acting on the magnet is not 0. F is not equal to 0. But torque here also may or may not equal to 0. Why? Because we can't say even it is non-uniform field. You can take another diagram. So field is like this. It is non-uniform field only. And if the magnet take in this direction, like this, non-uniform field, different fields here and here, north and south, definitely force is resultant force is acting on that. Why? Because here field is different, here field is different, then force is different. So net force must be act. But here you see, and one of the force acting like this, other force acting like this, it is not possible to rotate the magnet. Even non-uniform field is there. In some cases, it is not possible to rotate the magnet. So no torque acting. In some cases, torque is acting. Suppose here torque acts. So even though it experiences a force like this, so torque is acting. Okay. So in both cases, uniform field means net force must be 0. Non-uniform field means force compulsory acting. F is not equal to 0. But both cases torque may or may not acting on that. Okay. Now we'll see location of null points between two magnetic poles. What is null point means? Where a resultant field becomes 0. So where net field is cancelled and field is 0. Or otherwise, if you place a unit pole at a particular point, it doesn't experience any force. That point what we call null point. Suppose if you take two magnetic poles, M1, M2 are the strengths of the poles separated by a distance r, and assume that at a particular distance x from M1 and other from M2 is r minus x distance, there you get null point. What is the condition here? B1 plus B2 is equal to 0. That means magnitude of the magnetic field due to these two poles at this point are equal and opposite. So equate magnitude here. What is magnetic field induction due to first pole? That is mu naught by 4 pi M1 by distance from here to here x, that's why x square. Other magnet is r minus x, that's why you get r minus x whole square, you get other pole M2 by r minus x whole square. And cancel common terms, you get x by r minus x whole square is equal to m1 by m2, and make it root and for easy calculation this value you can assume like a, and after that solve x value. Finally we can substitute that a value here, x like this, and finally we get r by square root of m2 by m1 plus 1. Actually we are getting here plus 1. So if these two poles are like poles, both are north or both are south, then you can take here plus. One is north pole, other is south pole, unlike poles, then you take here minus. So here our square root is there only for m2 by m1 here. Now where you get location of null points? Suppose if both are like poles, both north or both south, definitely get null point between the magnets and nearer to the weaker magnet, between the poles and nearer to the weaker pole. So suppose here example you can take m1 is less than m2, where you get null point location means it is little nearer to m1. And if you take unlike poles if you take, and here you get null point outside. So another neutral point, here one neutral point, here another neutral point is there. So outside you get. Which side? Outside means this side also it is possible. But here m2 is greater than m1. So it is nearer to weaker pole only we get. Like poles means between, unlike poles means outside we get, and nearer to weaker pole. That is important here. Okay. So formula, when you take plus and when you take minus, like poles for unlike poles. Now we'll see location of null points between two bar magnets, and in previous case that is between two poles, isolated poles, and now between two bar magnets. And take two short bar magnets of magnetic moment m1 and m2, and centers are separated by a distance r, and assume that location of null point is x distance from first magnet and r minus x distance from second magnet. Here also magnetic field due to first bar magnet is numerically equal to magnetic field due to second bar magnet. That's why I equate here magnitudes. So this is the point on axial line now. So what you get? Mu naught by 4 pi to m1 by x cube. Here to here distance is x, that's why. From other magnet what you get? Mu naught by 4 pi to m2 by r minus x whole cube we get. So mu naught by 4 pi get cancelled, and you get x by r minus x whole cube equal to m1 by m2. X by r minus x equal to cube. You can send the